with Professor Hera, who's going to talk about that.
Thanks. Okay, so so first of all, I think I have to apologize maybe for the use of the word rough here. So it's not rough as in rough path, it's just rough as in not smooth. Okay? And so what I'm going to talk about is sort of joint work with, so there are some numerical bits that are mostly joint work with Jochen Voss. And there are some theoretical bits that are mostly joint work with Jan Maas. So the general philosophy here, so what I want to kind of explore is, there's this sort of folklore fact that if an equation is well posed, then, you perturb it in any sort of reasonable way, the perturbed equation should converge to the original equation if the perturbation is small. Right? Now, of course, it sort of depends on what you mean by well posed. So if you think of SPDEs, this is not really true, right? So if approximating the stochastic integral with sort of right-hand-sided discretizations is perfectly reasonable, and approximating it by centered discretizations is perfectly reasonable, and we all know that it doesn't converge to the same limit because, well, solution to SPDEs is sort of well posed in a stochastic sense, but it's not really well posed in the classical sense, right? Now, the question is, do you have similar kind of phenomena appearing in equations that are actually well posed in a classical sense? Okay? And so, for example, like SPDEs with additive noise. Okay, so I don't need any sort of fancy stochastic calculus to define solutions. And sort of surprisingly, the answer is actually yes under some circumstances, and essentially because of the spatial roughness of the solutions. Okay, so I mean, you can have SPDEs with very rough noise, so the solutions are very rough, and that there are some situations where the solutions are sufficiently rough so that approximations to your SPDE that appear perfectly reasonable actually don't converge to the limit that you would expect them to converge to. Okay. So the first example that I want to show you is the discretized stochastic Burger's equation. Okay, so so here G, okay, so stochastic Burger's is this equation here, so it's the heat equation. X is one-dimensional, okay, and think of it, say, interval 0, 1 with periodic boundary condition. The boundary condition don't really matter in this talk, okay? It's just easier if you think of it as being periodic. The nonlinearity here, okay, the usual Burger's equation is G of u equal to u, simply. And maybe you should just think of G of u as being u, but one can treat more general nonlinearities here of this form. And psi is space-time white noise. And it's very important here that it's really space-time white noise and not anything else. Now, this equation is sort of perfectly well posed because what you do is you interpret the nonlinearity here as actually the derivative of some function capital G of u, where capital G would just be the primitive of little g, okay? And then you can make sense of this equation by just hitting with test functions, in the usual way, right? Or in the mild form or whatever. And it's sort of well known at least since the early 90s, that this equation is well posed. So it has global solutions, well, maybe depending on G, but at least if G of u is equal to u, it has global solutions. There's no problem making sense of them. So now, what about numerical approximation? So if I write the equation in this form, it seems perfectly reasonable to approximate it like that. Right? So you evaluate the function on the grid. So I call epsilon here the spacing of the grid. So epsilon would be like maybe 1 over n. And, well, I have to discretize the second derivative. So there are several ways I could discretize the Laplacian on the grid. One way is just finite differences. And one way would be take the discrete Fourier transform, multiply by k square, and Fourier transform back. Okay, so that's sort of two reasonable ways of approximating the Laplacian. And then the nonlinearity here seems perfectly honest to approximate it in that way, right? So the g of u, I just evaluate g at the grid point that I'm looking at, and the derivative, I just discretize it by doing a finite difference. Okay, so I just evaluate u at the next grid point, take the difference with the current grid point, and divide by the width of the grid. Okay, and then here it's sort of well known that this 1 over square root epsilon is the right scaling so that this thing converges to space-time white noise. So the xi-n's here would just be independent white noises on every grid point. Okay? So, for example, if you forget about the nonlinearity, it's pretty easy to check that the solution to this equation, so without the nonlinearity, so g of u equals 0 if you want, do converge to the solution of the stochastic heat equation if you let the grid size go to 0. Okay, so that's essentially an explicit calculation here. Now, surprisingly enough, what happens if you let epsilon go to 0 in this discretization is that the solution actually converges to this equation with a constant c here. So you have an extra term that appears, which is proportional to the derivative of g evaluated at u. And the constant of proportionality, c here, actually depends on how you discretize the Laplacian here in the first place. Okay, so if you discretize the Laplacian by finite differences, then c is a quarter. If you discretize the Laplacian, so what I mean by spectral here is what I mentioned earlier, meaning you Fourier transform the solution, then you multiply by k squared, and you Fourier transform back. Then the constant c here is 0.19 something. So actually, this is the exact expression. To my knowledge, there's no better expression for this than this. And actually, if you just if you don't discretize the Laplacian at all, so if you just view this as again an SPDE on the space of continuous function, except that you replace the nonlinearity by g of u times u of x plus epsilon minus u of x divided by epsilon, then you get the same sort of convergence again with c equal to a quarter. But it seems to be some sort of bizarre coincidence that it's both times a quarter that shows up, in the sense that it doesn't show up in the same way. Okay, so that's the first example. The second example actually comes from a path sampling problem that we investigated together with Andrew Stewart and Jochen Voss. And so for toy model, so I'm going to show you the path sampling problem in question on the next slide. And this is really sort of a toy model for it. And so again, we start off with the stochastic heat equation. And now this time, we essentially perturb the stochastic heat equation instead of sort of approximating some nonlinear version of it. So we start really with the linear stochastic heat equation, and we add these two terms. So we change the linear part. We do a singular perturbation in the linear part here. Right? So we add an epsilon squared times a fourth derivative of u. And then we add a nonlinearity, which is sort of similar to before, except that it has an epsilon in front, and it's the second derivative of u that appears here, not the first derivative of u. Okay? Now, again, you would think, well, okay, it's not clear how to actually make sense. So it's not absolutely clear a priori that this equation is well posed, right, because of the second derivative of u here, and the fact that psi here is space-time white noise, so solutions, again, are not going to be very regular. But it turns out that because of the fourth derivative here, you gain sufficient regularity so that for every fixed value of epsilon, this equation is actually perfectly well posed. Yeah? And again, you can you make sense of it in the classical way by just hitting it with test functions, integrating by parts, etc. And right, so now what happens as epsilon goes to 0? So, right, I mean, naively, you would expect that these two terms, the two red terms, just drop out, right? And so it should actually converge to the stochastic heat equation. Even though, well, so the perturbation is kind of singular because you have high-order derivatives of u appearing here. But in classical singular perturbation theory, most of the time what happens is that still these singular terms just disappear. Right? Well, actually, again, it doesn't. And as epsilon goes to 0, the solution to this equation actually converges to the solution to this equation with an additional nonlinearity, which is pretty much the same nonlinearity as before, actually. And actually, even this constant 1/4 turns out to show up in the same. No, sorry. So the 1/4 shows up in a different. It's again a coincidence that it's 1/4. Proof that it could be coincidence is that there is a situation where it's 0.19. So. Yes?
Can you eliminate the first derivative to get the same?
If you don't have this term here, this equation isn't well posed, right? Because of because of the nonlinear bit here. So, okay, maybe. Well, it might be well posed for some g's, okay, but it's not necessarily well posed whatever g is.
If you take just kind of fractional derivative of slightly less order than 4, it would still be well posed.
Right, that's true. And then you would have similar sort of convergence, but you would have to take different powers of epsilon here. Right, so there's a sort of an interplay between, you know, the powers of epsilon that you have here and the order of the derivatives of the additional terms. So for example, if you added instead of a fourth derivative, you put a sixth derivative with a plus sign, then in order to get a sort of order 1 contribution in the limit, you would have to put an epsilon to the 4 here, and an epsilon to the power 1. Right. So, I mean, it's as usual somehow in multi-scale analysis, right? I mean, you need to get your powers of epsilon right so that you get an order 1 limit. So this turns out to be the right powers of epsilon. If you choose them differently, either the thing diverges or you don't have this correction term in the limit. Oh, and maybe one thing that's worth mentioning is that if you put constants in front of these terms, then the constant that would be in front of the g prime here depends on all of the constants that you put in front of all of the terms, right? So if you change the constant here, that shows up here. If you change the constant here, that also shows up here. Okay, so you can, if you change any of the constant, it actually shows up in this constant here. Yeah.
You said at the beginning that it really depends whether it is space-time white noise.
Yeah.
What you meant is that probably when you have a Wiener process with Kama-Martin space better than H1, you would get no
then you
correction.
would not, exactly.
But what if you had a Wiener process with Kama-Martin space
worse?
Even rougher?
Then again, probably it would depend, you know, then it's the same sort of game. You would have to change the powers of epsilon here.
But you still believe
So if you take the same powers of epsilon, then the thing would divert. It wouldn't converge to anything.
What happens if X is multidimensional?
If X is multidimensional, then again, the scalings would be different.
Do you have a theorem that goes?
But no. Okay, so now, okay, I promised earlier on that I would just explain where this comes from, because I mean, this equation looks sort of really cooked up out of nothing, but there's really a reason why one would want to look at these sort of equations. And so that's this path sampling problem that I looked at with Andrew and Jochen. So consider a gradient system. Well, in R, any sort of SDE with additive noise is a gradient system. Right? Every function is a gradient, so I write it in this form. Now, it's kind of well known that if you take this Smoluchowski-Kramers approximation, so essentially you add a second order time derivative with a small parameter epsilon in front, then the solution to this equation as epsilon goes to 0, converge to the solution to this equation, right? And this is sort of a natural singular perturbation of this. So if you think of it as being a particle in a potential with some friction and with some noise, then this would really be the second order dynamic in the overdamped case. So this would be really the overdamped limit, and this would be the case where you have somehow a very small mass, but still non-zero. Okay, so it's known that this converges to this. Now, what you can do is, well, so the path sampling problem is, suppose you want to write a computer code which generates a sample from the solution to this SDE, but conditioned not just to start at a given point, but to start at a given point at, say, time 0, and to end up at another given point at time 1. Okay? Then how do you do that? You can't just draw samples until you hit that endpoint, because you'd never hit it. So the idea there was, say, okay, I can find a stochastic PDE. So my original time, I now interpret it as space for the stochastic PDE, and I add a sort of fictitious algorithmic time. And I can write down a stochastic PDE, which has the property that the invariant measure for that stochastic PDE is exactly the law of this process here with the given initial and final condition. Okay? And then you can write your computer code by just running your stochastic PDE for a while, and then you hope that it equilibrates after a bit. That's, of course, the tricky part. And then you look at the solution, and that should be something that looks like the thing you want to simulate, right? Now, if you do that, so that's sort of reasonably well known that the stochastic PDE corresponding to this is actually given by that, right? So it's some sort of basically like a reaction diffusion equation. Okay? Now, the thing which is maybe a bit less well known, and that's actually the content of a recent paper also with Andrew and Jochen, is that you can do the same thing for this equation, for the second order equation. And then you end up with a fourth order stochastic PDE. Okay. Whoops. And the scalings are more or less the scalings of the previous slide. Right? So the epsilon here turns into an epsilon square in front of the fourth order term. And you have a term here that appears with an epsilon and some function of u times the second derivative of u in x. And then you actually have an extra term here with a derivative of u squared and also an epsilon in front. And now you see here, you would like to say, well, since at this level you know that solution to this equation converges to solution to this equation, well, you would expect that at the level of the SPDEs, the solution to this equation converges to the solution to this equation. And you see that if you just naively cross out all the terms that have an epsilon, you're missing this term here. Right? And that was kind of a mystery to us for a while, until we, kind of figured out how. Well, so then our first guess was to say, well, it should come from here, because here you have this derivative of u squared, and as epsilon goes to 0, the solution is not differentiable anymore, and so it might be that this blows up in exactly such a way to cancel this, and so this might contribute a third derivative of u, but then you realize that this has a minus sign and this has a plus, so you spend 3 weeks trying to find the sign error, and then after 3 weeks you convince yourself that you got all your signs right, and then it turns out that actually this term here ends up in the limit as well, and it exactly compensates that one. It's exactly twice as big as that one, and so it changes the sign. And it's again one of these stupid things that happen. Okay, so that's the two examples I want to talk about. Maybe now just a bit of sort of relating this to the rest of the literature. So I haven't really seen anything sort of like this, but there are lots of work that have similar flavor in a way, right? So, of course, the numerical approximation to stochastic Burgers, there are lots of works on numerical approximation of stochastic Burgers, so I mentioned here a couple of relatively recent papers. Then there are another sequence of works that have a very similar flavor, all these works about sort of renormalization for SPDEs that are not well posed. Right? Except that, so there, in some sense, it's harder if what happens is that you have infinite terms that appear and you want to get rid of these infinite terms. And in this case, in some sense, the terms that are infinite in these works, they're actually finite here, and so you don't need to get rid of them. They kind of appear in the limiting equation. But it's a very similar, the analysis has a very similar flavor to all these works here. And then there are, of course, also lots of works sort of on essentially the analysis of SPDEs that have very rough solutions. And again, I just quoted a couple of works, and there's much more, of course. So maybe before I go into the theoretical explanation of what I just told you, I want to present some numerical evidence. Right, so this first picture here is just to convince you that indeed you do have an order 1 effect coming from different ways of discretizing stochastic burgers. So what we did here is we took a fixed initial condition and a fixed realization of the noise, and we discretized stochastic burgers in 3 ways. So once kind of to the right, once with the derivative. So we discretized the derivative once to the right, once to the left, and once in a centered way. And we ran it 3 times with the same realization of the noise and the same initial condition, and you see the 3 solutions are clearly order 1 apart. And you actually also see that, so they are sort of ordered also vertically, in the sense that, you know, so the one with the right discretization is above the one with the centered, which is above the one with the left. And that makes sense because of the correction. If you do the same calculation for all 3 discretization, the correction constant that you obtain just changes sign between the right and the left discretization, and it becomes 0 for the centered discretization. And so, you know, you would expect the solutions to sort of lie on top of each other. Now, what we did here is we compared now these the same 3 solutions to the solution. Oh, so, yeah, sorry. The color coding is different here. So what we've done is we've run all 3 discretizations, and then we've also run the right-handed discretization, but we added an extra correction term which should then compensate for the one that we expect to appear in the limit, okay, in order to have as the limit the correct stochastic Burgers equation. And then we compared that solution here to the 3 discretizations, and it turns out that the centered discretization agrees almost perfectly with the right-handed discretization, where we added an extra order 1 correction term to compensate for the one that we expect to appear in the limit. Okay, and then again, if you take the other 2 discretization, you get something different. So that essentially tells you that we guessed the correction term right. And here, what we did is, so in order to just to show that these constants are 0.25, I mean 1/4 for the finite difference discretization of the Laplacian, and 0.19 for the other discretizations of Fourier transform multiplied by k² Fourier transform back. What we did here is we took the right-handed discretization and we added by hand the correction that's supposed to then give the right limit, but with an arbitrary constant, and we varied the constant. And then what we plot here is the L2 norm of the difference between that solution and the solution to the real limit. Okay, so just the solution to stochastic Burgers. And well, it should be 0 if you subtract exactly the right constant. Okay? And you see here, indeed, it's 0 essentially at 0.25, and here it's 0 essentially at 0.19. Yep.
Is this averaged or omega by omega?
This is omega by omega. It's just for actually one realization. The reason why it's sort of very nice and straight here is just because it's a, linear. Okay. So now why do you get this correction term? Or how can you guess the value of this correction term? Okay. So I'm going to do the whole explanation for the discretization of Burgers, and then I'm going to spend, say, one slide on the other equation, but you see it's really kind of the same thing. It's very similar. I mean, the details are very different, but the idea is very similar. So there are essentially two ingredients, two things that one has to realize. So the first thing is that there's really sort of a separation between the behavior at small scales and the behavior at large scales. So at small scales, the solution to a sort of parabolic SPDE like this essentially just behaves like the solution of the linearized problem, right? So if you look at very small scales, the nonlinearity just doesn't really play any role. Okay? So one typical kind of statement that one has is, for example, that the solution to stochastic Burgers equation belongs to the Sobolev space HS for every s less than a half, but it doesn't belong to h1 half. But if you subtract the linearized equation, then the solution actually belongs to every HS for s less than 3/2. So you gain one derivative worth of regularity. And, so that tells you that in the high wave numbers, the difference here is much, much smaller than the solution itself. And so that means that you can essentially replace the solution by the linearized equation. Okay. As far as the high wave numbers are concerned. In the low wave numbers, of course, completely different. Okay. And of course, the reason, so why do you gain exactly one derivative here? Well, essentially, if you're in h1 half, well, you're not in h1 half, but you're kind of, morally, you're almost in h1 half. Okay? So h1 half is just the smallest Sobolev space, which is still an algebra. So an h1 half function times an h1 half function is, again, an h1 half function. So the solution to the linearized equation is morally h1 half. It's not quite, but almost. So if you square it, you still get something which is essentially h1 half. Then you lose one derivative here, so you end up in h minus a half, and then you gain two derivatives because of the Laplacian, so you end up in h3 half. So that's where the 3/2 here comes from. So that's the first fact. The second fact is that if you take, again, a nice semilinear SPDE with additive noise, that lives in some, so here I write curly H alpha. So straight H alpha was just the usual fractional Sobolev space. Curly H alpha here is just the domain of a to the power alpha. Okay? So if the solution lies in some interpolation space, H alpha, and the nonlinearity here goes from H alpha to H alpha minus delta for some delta less than 1, okay? Then, well, here, y is not, so if the solution to the linearized problem lies in H alpha, and f is locally Lipschitz from H alpha to H alpha minus delta, then the solution to the original equation, to the nonlinear equation, also lies in H alpha, right? And furthermore, if you take an approximation to f, so if you approximate f by some sequence of nonlinearities f epsilon, in such a way that f epsilon approximates f well as a map from H alpha to H alpha minus delta, then the approximate solution converges to the solution to the limiting equation. Okay? Now go back to Burgers. So I can rewrite, so the point in the case of Burgers is that if you replace the nonlinearity, so let's take g of u equal u, so the nonlinearity is u times dxu. So if you replace this by u of x times u of x plus epsilon minus u of x divided by epsilon, then this is actually not a good approximation of the nonlinearity, in any space that the solution lives in. Okay? The problem is the solution lives only in H almost a half and nothing better than that. And as a map from H a half to H minus 1, say, so the nonlinearity itself, so the derivative of u squared, that's a perfectly nice local Lipschitz map from H a half to H minus 1. For example, it's actually even better than that, but say H a half from H to H minus 1, okay? Now, this finite difference approximation is a bad approximation of this map as a map from H a half to H minus 1. It's a very good approximation as a map from, say, H2 to H1 or H5 to H4. So in the deterministic case, there's no problem because the solutions become C infinity straight away. They lie in every Sobolev space. And then in the higher order Sobolev spaces, it's actually a good approximation. But as a map from H a half to H minus 1, it's a very bad approximation. Okay? And that's why this argument actually doesn't apply. Okay? Now, on the other hand, I can rewrite, so that's a very simple sort of first-year algebra, that un times un plus 1 minus un divided by epsilon is equal to this here. So this blue expression plus this red expression. Now, the blue expression here, that one is a good approximation of the nonlinearity as a map from H a half to H minus 1, right? Because here, it's a difference of it's a difference of a function of u evaluated at n plus 1 and a function of u evaluated at n. And so if I view this as an element in H minus 1, means really I have to integrate against some nice test function in H1, then I can do some sort of discrete version of integration by parts in order to get rid of the derivative and hit the test function with it. And so this is a perfectly nice map, right? So essentially, this part here is a good approximation of the nonlinearity. But then there's this extra term here. Now, if the solution was smooth, then this should go to 0, right? Because this is something like a derivative squared, but times epsilon, because the derivative would be un plus 1 minus un divided by epsilon. If I square it, I should have an epsilon squared, but I only have 1 power of epsilon. So this is something like epsilon times the derivative of u squared. Okay, so again, if u was smooth, then epsilon times the derivative of u squared would go to 0. But u is not smooth. Okay, so the regularity of u is essentially that of Brownian motion in space. Okay, and now Brownian motion in space, of course, has non-zero quadratic variation, and this here looks very much like the quadratic variation of the thing. Okay? And so it's maybe not surprising now that if you pass to the limit, this term here actually gives us sort of an order 1 contribution, which is something like the local quadratic variation. But then the problem is that this is actually the local quadratic variation at a scale at which you have also approximated the Laplacian by something else. Okay? And so it actually messes up what happens at these scales, and that's why what you get really depends on how you actually discretize the Laplacian. Right? So what you can do in order to guess the contribution of this term is replace in here u by v, which is the solution to the linear problem, or to the approximate linear problem, so the one where you approximate the Laplacian by whatever you want to approximate it by. Okay? And then compute the expectation of this term here for the solution to the linear problem. Okay? And it turns out that if your approximation has eigenvalues lambda k epsilon, then this here, you can just do the calculation, you get this. And now, in the case of the finite difference approximation of the Laplacian, it turns out that lambda k epsilon is also cosine k epsilon minus 1, and with some 2 pi's and numerical constants floating around, but essentially it's the same term here, so these two terms cancel out, and so you just get a sum of 1 with sort of a certain number of terms. So you can compute the limiting constant, you get this 1/4. And if you take a different approximation, so if you take the Fourier transforming multiplying by k square Fourier transforming back approximation, then here you have something like a k square, well, it's really k square epsilon square, maybe divided by n or divided by n square or something like that. And then in the limit as epsilon goes to 0, this sum essentially becomes a Riemann sum, and that's why the correction constant was this integral of cosine x minus 1 divided by x squared. Right? So the x square is the k square, really, and the cosine x minus 1 is what's left over from this term here. Oh, and in the case where you don't approximate the Laplacian at all, then you have exactly the same as if you do the spectral approximation, except that the sum here runs up to infinity. And so it's essentially the integral from 0 to infinity of cosine x minus 1 divided by x squared. And that, by miracle, is the same 1/4 as the 1/4 that came out before, but it really comes out in a completely different way. Okay, and then one has to argue, of course, that it's really only the 0 Fourier mode that counts. So this expectation is really something valid to do. But in here, there's no expectation, of course, right? And so why would you be able to replace this by its expectation? Well, so that's part of the technical details. I don't want to go into that. Right? But it turns out that essentially all the Fourier modes of this term that are not the 0 Fourier mode, they are individually, they are small. And so they would add up to a large contribution if you kind of summed them all up, but then they get damped by the linear part of the equation, and so they add up to something small at the end. Okay, now in the case of the equation that comes from this path sampling problem, or at least the toy model for this path sampling problem, you can do a similar sort of analysis. So what you do is you look at the linearized equation, but this time you look, again, the linearized equation depends on epsilon, so you add this epsilon squared dx4 term into your linearized equation. And now what you notice that the linearized equation actually belongs to, the solution to the linear equation actually belongs to all the Sobolev spaces up to 3/2, but it's of order 1 only in Sobolev spaces up to 1/2. So in the Sobolev spaces between 1/2 and 3/2, the solution is of order some negative power of epsilon. So it's actually epsilon to the power 1/2 minus s, where s is the order of the Sobolev space for s between 1/2 and 3/2. Okay, which is not surprising, because if you drop the epsilon, then the solution actually belongs only to every Sobolev space up to 1/2. Okay. So between 1/2 and 3/2, you get some negative power of epsilon for the size of the solution. And so now the nonlinearity here, so this g of u times the second derivative of u, I can rewrite it as the derivative of something minus this term g prime of u times the derivative of u squared. Okay? So that's just simple algebra. Now, the derivative, now again, if you believe that u behaves like v in terms of regularity, okay, then what one should believe is that the derivative of u should be of order epsilon to the minus 1/2, right? Because that was the case s equal to 1. If for s equal to 1, the hs norm is of order epsilon to the minus 1/2. Okay? So the L2 norm of dxu, which is really the h1 norm of u, you would expect it to be of order epsilon to the minus 1/2. And therefore, you would expect this term to be of order epsilon to the plus 1/2, at least in h minus 1. Okay? And so that term you would expect it to just drop out in the limit as epsilon goes to 0. Whereas the remaining term here has a derivative of u squared. And so since the derivative of u is of order epsilon minus 1/2, the derivative of u squared is of order epsilon minus 1, which exactly cancels out the epsilon to the power plus 1, which is here. Okay? And so you would expect this term to still have an order 1 contribution in the limit. Okay? And again, in the same way as before, you can guess what the contribution should be by essentially just replacing u here by the linearized equation, taking the expectation and seeing what you look at what you get. Okay, then you get this constant 1/4 that popped out. And now, of course, again, this term by itself, it doesn't converge to a constant at all. Okay, but what happens is that so if I draw a cartoon of what this, so epsilon dxu square for epsilon, if I plot this as a function of x, what you expect this term to look like, so here is something order 1, is something that sort of oscillates wildly. Okay, it sort of looks like this, morally, with the width here of the oscillations of order epsilon. Okay? So the average value here is something you can compute. So that's what you get if you just plug in the solution to the linearized equation and take expectations. Okay, then you compute the average of this function here. Of course, the function itself actually oscillates like crazy, but it oscillates really, really fast, which means that on every sort of very small interval, it essentially averages out to its mean value. Okay. So what that means is that if you multiply it by some function of u, which is at least reasonably regular, and now, of course, here come the tricky and dirty details. But if you multiply this by some reasonably regular function of x, then, well, what you get is this very rapidly oscillating thing modulated by, this function of x. But then it gets hit by, if you write down the solution to your equation in the mild formulation, it gets hit by the semigroup. And the semigroup acting on a function like this, what does it do? It sort of multiplies it. It takes the convolution with some very nice kernel. Right? And so taking the convolution with a very nice kernel essentially smoothens out all these crazy oscillations here. Okay? And so since these oscillations, they average out to the average value on a very small scale already, when you smoothen this out, so when you integrate this against the heat kernel or whatever the kernel of the linearized equation is, these oscillations disappear. And so that's why in the limit, the solution that you get is the same as what you would get if you just replace this by a constant. Okay. And again, as a remark, so if you look at this nonlinearity here, for those of you who are sort of familiar with stochastic Burgers and KPZ, it looks very much like the KPZ. I mean, it is essentially the KPZ nonlinearity. In the case where g prime of u is a constant, this is really the KPZ nonlinearity. So again, it's sort of very similar to the analysis of KPZ equation, but it's easier in a way because this term here, which in the case of the KPZ equation blows up, and so you have to do a whole renormalization procedure. Here it doesn't blow up because it still has this epsilon in front, which exactly compensates for the blow up. Okay? So that's why there's a sort of, it survives as an order 1 term instead of being an infinite term that has to be renormalized. Okay, now what can we show rigorously? Okay, so I've told you a whole story here. It's partly made up of rigorous results, partly made up of work in progress, partly made up of conjectures. Okay? So rigorously, one can show for the moment, for example, that if you take stochastic Burgers, you don't do any discretization of the linear part, and you just replace the nonlinearity by this finite difference quotient here, then the solution to this equation converges to stochastic Burgers with a correction term. Now, so what's the sort of technical problems that appear in the proof? So the one technical problem, which is actually much trickier than it looks like, is to get a priori bounds on the solution to this equation. Because you see, the reason why it's quite easy to get a priori bounds on burgers is because the nonlinearity preserves the L2 norm. Now this thing doesn't preserve the L2 norm anymore, okay? And it has a 1 over epsilon in front. And so since this is a quadratic term that doesn't preserve the L2 norm and has a 1 over epsilon in front, if you just do the brutal kind of estimate, a priori estimates that you would like to write down on a sheet of paper in 2 minutes, then it would tell you that you have finite time blow up, which comes earlier and earlier as epsilon goes to 0. So as epsilon goes to 0, the bound that you get is, well, the thing blows up immediately, right, which is not very good. And so just to actually get a priori bounds on this equation, you already need to know what's going to happen, actually, right? So you already need to sort of play with this nonlinearity to write it in the form that I wrote down earlier, and make an argument that says that this u of x plus epsilon minus u of x squared divided by epsilon term is actually of order 1 and not of order 1 over epsilon. And so you already need to do quite a bit of analysis just to actually make sure that this equation doesn't blow up immediately. And so after that, what you obtain, at least the best bounds that we've been able to obtain, is the equation still might blow up in finite time, but that finite time actually gets pushed further and further into the future as epsilon goes to 0. And that's what you want. Okay? So in the sense that if you take any finite time horizon and any probability delta, for epsilon small enough, the probability that it blows up in that time horizon is less than delta. Okay, and you have sort of a reasonable control of how delta depends on epsilon. And then the other thing you have to show is that even for the linearized system, somehow this difference quotient really behaves like a constant in a sort of sufficiently controlled way. Okay? And for this, what we use is essentially Gaussian concentration inequalities, sort of a la Borel-Sudakov-zero sum. Okay, so by using Gaussian concentration, you can get somehow a very good control over the behavior of this term. Right. So just to conclude, there are still quite a few open questions, but still, as I told you, part of what I told you are just stories or conjectures that are sort of, we have good numerical evidence, one has very good hand-waving calculation that show what's going to happen, and one has some proofs and some almost finished proofs. Then one thing is what happens about multiplicative noise. Right? So if instead of having additive noise, I had a f of u times dw in the noise, then one can still sort of guess what the answer would be for these correction terms. So then it should be really, again, you can guess what the answer should be by essentially seeing what happens for SDEs. So it is really like a sort of Ito-Stratonovich correction term, but in space instead of in time. But you can make an educated guess as to what you should get, but all the arguments that we have for turning what I just told you into proofs don't work at all, okay? Because you cannot sort of break the equation into the linearized part and some smoother part and then, analyze the linear part separately. That simply doesn't work for multiplicative noise. Then another thing is in the case of the stochastic Burgers, so what happens if the function takes values in Rn, and this function g, so remember in the case of stochastic Burgers, your nonlinearity was of the form g of u times derivative of u, and the point was that one rewrites this as actually a derivative of g of u if one wants to make sense of this equation. Now, if u takes values in Rn instead of taking values in R, you can't always do that, right? You can do this only if g itself is a gradient as a function from Rn to Rn. Okay? Now, what happens if G is not a gradient? So, well, one thing you could say is, well, okay, then I just don't know how to make sense of the equation. Now, if you do it numerically, nothing bad happens, right? I mean, there's no blow up or anything like that. And we have reasonably good arguments to say that this equation should actually be well posed, even if G is not a gradient. Okay? But it's certainly not well posed in the kind of classical sense. Right? So you couldn't apply any of the classical theorems from stochastic PDE theory. Okay? So the reason is you can't do the integration by parts, and this product in some sense is really like a stochastic integral in space, right? Because the solution behaves like Brownian motion in space, so this is like white noise in space. Okay, and so when you hit this with the semigroup, you want to integrate this against some kernel, and this integral is something like a stochastic integral in space, okay? Which should be of order 1. So there's no reason for this to blow up. Okay? But the integrand is not adapted, and so on. Okay, so it's a tricky object. But one has reasonable arguments to say that this should be well posed, and that again, depending on how you discretize the derivative here, you'll get correction terms appearing, and we've checked these numerically, and they are the ones that you would expect. Oh, and then finally, so what happens in even rougher noise? So one of the sort of far out in the future goals of this sort of project would be to also try to better understand KPZ. Okay, so right now KPZ is understood mostly through the Hopf co-transform. So you transform it back into a linear equation, then you understand the linear equation, but you don't really understand the equation you started from. Okay? So the aim is to actually understand really KPZ, but then you need 1 degree more of roughness. Okay, so well, we're not really there yet. Okay, thank you very much for your attention.
Any remarks, questions, comments?
As for the Burger's equation, have you proven it really rigorously for arbitrary G, or is it just for G equal to U, G of U equal to U, as you showed in one?
Okay, for the moment G of U equal to U, but we're working on sort of generalizing the argument, and it doesn't seem to be a huge problem to generalize the argument.
There will be many opportunities. Well, we have a coffee break now. Thank you very much.